Last time we talked about section 10.1 where we introduced the idea of these parametric functions. We did a bunch of examples. I asked you to work on or start working on 1 through 40. We'll start with some questions if you guys got anything. Emma, we'll go with you first. 17, sure. So this one is actually not so bad because the interval for the parameter is pretty nice for us. So there's got the t by itself, and then we'll take our equation for y and plug in this new value for t that we just found. And I'll FOIL that out. Remember, x minus 2 squared is x minus 2 times x minus 2. So that's going to be 2x squared minus 8x plus 8 plus 3 is plus 11. So that's my Cartesian formula. To get the domain, we're going to look at the x of t function, where t is defined over all real numbers. So the outputs of x of t are the x coordinates. I notice that x of t is what kind of function? Linear. And since the domain for that linear function is all real numbers, the range must also be all real numbers. Oops. So the domain for this is going to, our Cartesian function is also all real numbers.
So what did you have to do to get 2x squared minus 8x?
I've just FOILed out the step before it and combined like terms. So my range then is going to be using this guy. When I look at y of t, what kind of function do I notice this is? Try again. Quadratic. And is that quadratic, what does it look like?
It's a parabola that's going like positive, like
yeah, opening up, we would say. So the range there is going to go from the vertex to positive infinity. Everybody's up. So we need to find the vertex. So remember to find the vertex. Yesterday we said for ax squared plus bx plus c, well, f of x equals that the vertex is negative b over 2a, comma, f of negative b over 2a. So in our case, the vertex would just be 0 over 2 times 2, which is 0. And that's definitely, we care about it because it's 0 is inside of our interval.
So you don't use like the original Cartesian equation that you found,
I use this guy.
Okay,
Because that's what's giving me the y values, right?
okay.
So that's what I need. So if I do that, 0 is in there. So if I do y of 0, that comes out to be 3. So we're going from 3 to positive infinity because our guy is pointing up. Does that feel okay there, Emmers?
Yeah, I just messed up the vertex.
No problem. Nico.
For like a question like 21, where when you find the Cartesian equation and it's like a giant square root over everything,
Yeah.
how would you find the minimum or maximum for the domain? Because it's like the vertex, but it's sideways.
So 21. is what we're talking about. So I'm going to be using this, this equation to find the domain. So I'm just going to be using the vertex of the parabola. So in that case, the vertex again is at 0. So x of 0 would be -1. So that would be -infinity to -1.
Okay.
Should be the domain for that, since it's a downward facing parabola. Is that okay?
Yeah. Thank you.
Yeah. It was a very specific question, so I felt like talking was okay, then writing it down, you were good?
Yeah.
Okay. Mia!
Can you do the domain and range for 19?
For 19?
Yeah.
Sure. Okay, actually, I'll just move this over. I got the problems over here in my packet. All right. And so I'm going to skip the eliminate the parameter step because you said that you don't need that. So what I have here is what kind of function? Linear function. So if I were to graph this, here's my t-axis and my x of t-axis. This line has a positive slope and a y-intercept of 4. So it's going to be like something like that. So to calculate the range of this, all I really need are the endpoints of my graph. So I just need x of -2, which is 0, and then x of 4, which is 8. Okay, so my domain then should be from 0 to 8. Is that okay? Do you want to do the range also?
Yeah.
And then here, our range is a quadratic. So this quadratic is pointing down. The thing that I have to worry about here is like, do I have a situation like this where the vertex is in between the endpoints, or is the vertex outside of the endpoints? Because again, if it's this situation, I just need those 2 points. So the endpoints, those are easy to get. So that's what? 4, -13. So 16 times 3 is -48, so -49. Okay. And then the vertex, again, -b over 2 times a. So that's 0. And then y of 0 is just -1. So my smallest number amongst those 3 is 49. The biggest number is -1. And I know I need that because 0 is in between, or is on the interval for t. So it is the picture that I've drawn. So we should be going from -49 to -1. Is that doing okay for you, Mia? Follow up on this? Okay. All right, Paul, what's up?
Could you do 38?
Sure. So 38 says that we want the parameterization for a circle whose center is 0, 0, and whose radius is 2 root 3. Okay. So if we go back to yesterday, I'm going to use this example to kind of justify what I'm about to do. So remember yesterday we saw that 3 cosine t, 3 sine t gave us a circle whose center was 0, 0, and whose radius was 3. So I'm just going to kind of use this as my backwards map then. So I want, my radius needs to be 2 root 3. Oops. So I'm going to do that. And the 2 root 3 actually can be positive or negative there. It doesn't matter. And then we'll just tack on our cosine t and sine t onto that. And our interval for t, I would just write as 0 to 2 pi. Yeah, so it's covering the whole unit circle. Now, if your interval is longer than 2 pi, that's still fine. It'll just trace over the circle that you've already drawn a little bit more. If you had, so it's like if I draw, so if I go 0 to 7 or something, it would do like that, or it just like draw a little bit more, but it doesn't matter. It's just like tracing over something that's already drawn. It's fine. So it's starting at 0 radians. It goes all the way through 2 pi radians, and then just keeps going because it's a circle. It just keeps drawing that circle over and over and over again.
2 pi is a small circle you got.
Yes, 0. So as long as that interval is at least 2 pi long, the interval is correct. You could say all real numbers there, and it's not incorrect.
I see what you mean now.
It'll just keep drawing that circle over and over and over again.
2
But
pi is a circle.
yeah, because you're drawing a circle.
That makes sense. Okay.
So that's it. That's all we really need there. And you could have one of these intervals open even at either 0 or 2 pi. That's fine, because remember 0 and 2 pi are at the same spot on your unit circle, right? They're both right there. But you couldn't have both of them open, right? Because then you'd have a circle with a hole right at that spot. But almost anything you put as an interval there is going to be okay. I mean, if you did 0 to 7, that's fine.
Right.
You know.
So what happens if like the center is 0, 0? Like, I don't understand what you're doing with that.
Oh, well, that's means that I don't have to muck around with this stuff anymore.
Oh, okay.
So the radius is telling me what's going to come out front, and the center means that I don't have to do anything to the sine or cosine.
Okay.
Any translation there at all.
If the center was like 5, 0?
If the center is 5, 0, I think all I need to do is like add or subtract 5 to these or something.
Oh, okay.
Let's just take a quick look. I'm trying to remember exactly. Are we still in function mode? Okay. Do that. So let's try this real quick. So I'm just going to do like 3 cosine t, and then like plus 5. Let's just do plus 1. And I'll do 3 sine t. And I think that's just going to move it 1 unit to the right, so the center should be at 1, 0 now. Oops. Ugh, shut up. Zoom standard. 0 to 2 pi, okay. Oh, that's why. Look what I did. Mr. Kulik, you're so stupid. I have one of the equations written in one, and the other one in the other one. Like, what a dummy head. That's a good one for you guys to see, though. Like, what happens if I accidentally write half of it in one function, half of it in the other function? So yeah, that looks like what it did, right? It just translated it right 1 unit. So really, if we wanted to, we could say that in general what this is. So it's r cosine t plus h. And this is r sine t plus k. Just to make it general, right?
Yeah.
So if you think about it, if we just tack a +1, we're just adding 1 to every x coordinate in the circle. Shifts it 1 unit to the right.
Okay, just add.
Yeah. Emma's.
Yeah, use question.
Yeah, go for it, dude. Anybody else questions on this stuff? Ames.
Could you do number
4?
Yeah.
Yeah, so just want you to do this in the calculator, right? The directions say use your calculator to sketch the graph. So I have, what does it say? Sine t minus t cosine t times cosine t. Okay. And then I have cosine t plus t sine t. Cosine t plus t times sine t. And it says we want to graph this from -2 pi to +2 pi. So I'm going to go to my window and change my t-min. And then I think we're just ready to hit graph and see what we get here. Whoa, look at this crazy looking thing.
Oh my God.
Pretty neat.
There was one of them that we got that was like
Yeah.
that was
When we do the polar functions, you can see how you get like all kinds of flower shaped stuff and all kinds of cool things.
cool. Are we gonna like 3D graph?
Not with this stuff. We did a little tiny 3D stuff with the vectors, but that's all the 3D graphing that we're going to do in this course.
Like if you do AP Calc, when we do stuff where it's like you do equations and we plug them in, it's like 3D graph calculated.
Well, your calculators that were told you to buy don't do 3D graphing.
Like this.
Well, you
I
have
figured it out. It's
yeah,
so cool.
you
Like,
have the
I can-
fancier one.
I can make a code and like it's like a box and like you can do stuff with it. It's sweet.
Yeah.
I just figured it out. I was like, I had to Google how to do this, and like it also showed me how to like 3D graph. So I was like, whoa.
That's neat.
I thought it was pretty sweet because it could 3D graph in this mode and in like regular mode, and there's another one. But
Ames, you good? No problem. Anybody else before we move forward? Okay. Radical dudes. Let's talk about some applications now for these parametric functions. The most obvious application is going to be into the realm of physics. Because if you think about motion in general, if you're talking about, like, say you load a cannonball into a cannon and you shoot it, and you're trying to figure out the position of the cannonball, the position of that cannonball depends on how long it's been in the air, basically, right? So t is like your parameter, or time is like your parameter, t. And the position of the cannonball is like an x and y coordinate, so you can very easily translate most physics problems that deal with kinematics, the study of motion, very easily lend themselves to this parametric format. So we got one-dimensional motion. So I'm going to give you an equation for both position, which is S, and then velocity, which is V. Velocity, again, is basically the same thing as speed. It also has a direction to it. In physics, speed doesn't have a direction. Velocity can have a direction. So S, since this is one-dimensional, is basically just height. V naught is initial velocity. T is time, usually in seconds. It's going to act as our parameter. S naught is our initial height. And G is our gravitational constant. Typically in this class, we're going to be working in English units. So our gravitational constant in feet per second squared is -32. So really this just becomes so all we've done there is just filled in -32 for G and simplified those equations. And it's approximately. Physics students among us know in metric units, gravity is about 9.81, depending on how precise you're looking. Maybe even use 10 if you're really being lazy. Ugh. Can't stand it. That's physics trying to make math easier. It's like you have calculators. It's fine.
Mr. Bill, I think, uses like 9.82, and on the AP exam, we use 10, so.
Yeah. I don't know.
I think that's why we use it.
Probably, but that's an example of physicists trying to make the math easier for like reasons that become unclear. All right.
Thanks, Dave.
So at least reasons to me that are unclear.
Oh, you're right.
Like we all have, fancy calculators. We can handle like a couple of decimal places. It's no big deal.
Yeah, most of the time we have decimal place anyway, so.
Yeah. What's real obnoxious about that is if you're using that and you're actually doing sig figs, how many sig figs does 10 have? 1. And if you're multiplying, which you almost always are with it, how many sig figs should that answer give you? 1. And how meaningful is that? It's like, oh yeah, 1,346. Rounded to 1 sig fig. 1,000.
Also, for the gravitational.
Feels like I lose a lot.
With the gravitational constant, we tweak that a little bit too, so.
Yeah, I'm sure. All right, so let's do some examples. So let's say we have a ship stranded in the ocean. On top of the bridge is 80 feet above the water. Somebody shoots a distress flare straight up with initial velocity of 72 feet per second. Provide a graph of the flare's height against time and find the height of the flare above the water at the following times. So what are we looking for here? Heights, right? So which equation do I want to use? The position one or the velocity one?
The
Position one. So what's the initial velocity?
72 feet per second.
Great. And what's the initial height?
80 feet above the water.
So we could write it like this as just a Cartesian equation, which is kind of what they gave us. So I do that. There's my Cartesian equation. Set my window for time. Well, 0 and I got to cover at least 5 seconds. I'm going to go all the way to 10 maybe.
Can you use parametric with this?
We'll get there. The height of this thing, well, again, the flare height can be 0 at most. And I don't know, we're starting at 80 feet. I'm going to go up to 200 or something. Seems reasonable. Hit graph. So there's my graph of height versus time. Okay. And if I want the value at those specific times, if I press second and graph, I open up the table, I can just copy down at 1 second. It's 136 feet up. At 2 seconds, it's 160. At 4 seconds, it's 112. At 5 seconds, it's 40. You know, and those are above the ocean, obviously. Right? So, like, easy, no problem. But if I look at that graph, is that actually what I'd be seeing in real life?
Probably not.
No, what's the flare doing?
It's almost up and down.
Up and then straight back down, right? So this graph, while, yeah, there's a height versus time graph, but it doesn't really describe the motion that the flare is actually doing. To do that, we would use a parametric function. So maybe we'd start by just writing the parameterization of what we have here. So to do that, we'll just make x our t, and then negative 16t squared plus 72t plus 80. And check my window here. What did we say? 0 to 10 seconds. That's fine. Then we went 10 seconds in the x direction. That's fine. And we did 0 to 200 right on the y. So there's the exact same picture we had before, right? But what I really want is this to be a graph of position, like where the x is the like left and right, and the y is the up and down that the flare is actually doing in real life. So I'm just going to fix the x coordinate to a value since the flare is shooting straight up and down. Doesn't matter really what value I pick. I'm going to pick 1. So if I hit graph now, I get this vertical line.
Oh, so you're doing second.
But
You're saying for 1 second? That's
no, that's just fixing the position that we shot the flare at, is position x coordinate 1. But if I go over here, see this little option over here next to it, and I press enter a couple of times, I get this one with the little circle. If I hit graph now, what this is doing is that's actually what the flare is moving in real time. Was that pretty neat or what? Hit graph again. That should do it again. No, it didn't. Yeah, Emma.
What is the window again? Like what window should we have?
I did 0 to 10 on x and then 0 to 200 on y. So again, it doesn't matter what you pick the x coordinate as long as it's a constant. So if I do it at 2, it's the same thing. That's just describing the motion of the flare. And each, over the course of 10 seconds or whatever, which is pretty neato, right? That the parametric function can actually describe for you exactly the motion that the flare is taking. Pretty cool, Mr. K, pretty cool.
What's that little circle thing called?
I don't know, it's just like a cursor or something. I don't know, it's just in the y equals menu. I go over here and I have options. So I can make it graph in a dashed line, my standard solid line. I can do a thick line.
Oh, okay.
I can do a trace and draw the line, or I can just trace, which is often what I want to do for parametric motion stuff. Okay. So that's that. If I want to do two-dimensional motion, though, there is not a way to do that without a parametric. So let's call this S of t. Let's do that. Okay, so here's our two-dimensional motion equations. What do you notice here right away? We got a vector in here. Oh no! But really, what do the vertical bars around the vector mean? Magnitude. So the magnitude of a vector is just a number, right? And remember, if I wanted to resolve vector v into component form, I guess we'll call it v naught. So really, what do I have here? But just the x component of my velocity, of my initial velocity. And right here is just like the y component of my initial velocity. Basically, in the problems you're going to see, you will not really have to deal with the vector idea. Let's do an example. Sound good? All right, my baseball fans in the room. You hit a baseball 3 feet above the ground with an initial speed of 135 feet per second at an angle of 16 degrees above the horizontal. Will the ball clear a 15-foot fence that's 300 feet away? If yes, by how many feet? If no, how high up the wall will the ball hit? Okay. What do we need here? Position or velocity? Position. Very good. Okay, so the x-coordinate should be the initial velocity, which was? Very good. Cosine of theta. What's my theta? 16. And y of t, negative 16t squared, plus initial velocity, which was 135, sine theta, which was 16 degrees, plus the initial height, which was 3, right? Because the ball starts at 3 feet above the ground. That's the initial position of the ball. Everybody feel okay there? So what we're going to want to do here is we need to figure out how long it's going to take the ball to reach the wall. let's call that T sub W, the time it takes the ball to get to the wall. And then I'll just take Y of TW and compare that to the 15 feet. And I should be able to tell if the ball clears the wall or not, and then like how high up the wall it would hit. Does that make sense to you guys? So the tricky part here is going to be the first part, finding how long it takes the ball to reach the wall. How far away is the wall? 300 feet. And what direction is that? Vertical or horizontal? Horizontal. So I'm going to put the 300 in place for X. And use that to solve for T. Absolutely. You're welcome. So far, so good. Let's do this. I'm going to type this in here also because we'll look at the graph in just a second. Anyways, 300 divided by 135 cosine 16. Notice that I'm using the fraction command to do that. And if I press enter right now, that doesn't seem right. What's wrong with my calculator? Yeah, we were in radian mode from graphing. Very good. So I'll just switch that to degree mode and try it again. So 2.31-ish seconds. That sounds about right. Emmers, what's up?
Okay, so how did you know that it was horizontal?
So here's my picture, right? I got like the ball sticking up here. Here's the 15 feet wall. And it says it's 300 feet away, right? So how far is the ball from the wall? 300 feet in the horizontal direction, right? That's my picture. And we're hitting a ball, whoop, something like that. So all I need to do then is y of this 2.31. So I can plug that in by hand. Barfaroni. I mean, you could if you want to. That's a lot of typing for my liking. Or what I'm going to do, I'm going to have my calculator plug it in. So I put my equation for y into y2t. So if I press the vars button, and go over to the y vars, and we're working in the parametric function option, and I pick y2 of t, I can say, okay, what's y2 of t of my answer? It's 3.5 feet. Again, that's what you get if you plug 3.1 in to the equation for y, what I wrote down there. I just used my calculator so I didn't have to type everything all in. So did the ball get over the wall? No, right? That's less than 15. Baseball players, is that catchable? Seems like it, right? 3.5 feet above the ground. You ought to be able to catch that. All right. Would it be nice if I could look at the graph of this and be able to tell if it cleared the wall or not? Yeah.
Yes.
So like, let me do this here real quick. Baseball players, how long you hit a 16 degrees? It's a line drive-ish. It's going to go 300 feet or more. How long is that going to be in the air?
Seconds.
I don't know, 4 or 5 seconds maybe. That seemed reasonable for a non-pop fly. Okay. The X, it's going 300 feet, so I'm going to make that a little more than 300, say 350-ish. The Y, well, this is pretty line drivey, right? So, I don't know, maybe we go 50 as the maximum height, right? That's pretty, 16 degrees is a pretty flat shot.
Yeah.
All right. So I hit graph. This is what my baseball shot looks like. Would it be nice if I could get the wall to show up there so we could actually see it and like,
Yeah, that's a line shot.
yeah. Well, I can do that. So the X I'm going to put in as 300. And this is how I'm going to get the wall to show up. I'm going to do 15. That's the height of the wall, divided by T max. So to do that, I'm going to press vars. And then the T max is in the window. And then we're in the parametrics because I need a T thing. So I get T max right there. And then I need to divide it by, and then I need to multiply by T. Okay. And let's do this one in the cursor. And we'll see what happens. So there's my wall. There's the baseball. Oh, didn't quite clear it. That's pretty neat, right?
I like that.
Pretty neat, Mr. K. Pretty neat. Let's do another. Let's see what my main man Jeff can do here. Jeff hits a baseball at 3.5 feet above the ground with an initial speed of 141 feet per second at an angle of 24 degrees above the horizontal. Will the ball clear a 20-foot fence 400 feet away? If yes, by how many feet? If no, how up the high will the ball hit? So we'll do the same thing. We'll have initial velocity, cosine theta times t, negative 16 t squared plus initial velocity, sine theta times t plus initial height. So let's take a look graphically what's going on. So our wall's 400 feet away, 20 feet high. 141 is our new velocity. 24 is our new exit angle. So let me just go update those couple of things. 141 sine 24. And this is 3.5. Jeff's a little bit taller there, I guess. So if I hit graph, let's see what old Jeffy boy can do here. Oh, stop. I need to readjust, right? Why? Well, one, the fence is further away. It's 400 feet away. Two, Jeff's hitting that ball further up in the air. That angle is a little bit higher. So I'm going to adjust, oops, not that thing, Mr. Kulik. I want the Y max to adjust. Maybe they make that 100. And probably the ball's going to be in the air a little longer. Maybe I'll make that 8 seconds or something, because there's a little bit more pop-up-y. So there's my wall. There's Big Bopper Jeff's hit. Whoa, he's got a dinger.
There we go.
Way to go, Jeffy boy.
Unless you have that really tall guy back there.
Yeah, unless you got a 20-foot tall player,
Yeah.
I think you're in good shape.
Or he's just got really good hops.
Or he's got, like, just athleticism, like robotic, cybernetic level
He might be running up
athleticism.
that wall, I mean, like, or he could just do math like crazy and he knows where it's going to be. He's like, counting lines, like, oh,
Unless there's a door in the wall for him to go on the other side of to
yeah.
catch the ball, I think he's in good shape.
Or he like does that thing where he throws it in the air, catches the zero.
Does that, baseball players, is that legal?
If you throw it, I think if it doesn't hit the ground, you still have to catch your baseball.
That feels fishy to me.
Well, how hard is it to throw your mitt up and then catch your mitt once the ball's in the mitt?
Well, here's the thing. I've never seen a Major League Baseball player try to throw their mitt at a home run ball.
Because it usually doesn't work. And they're lazy, so they didn't practice it.
I'm not sure I believe you, Paul. I'm just going to say that.
It's alright, I get that a lot. So.
Okay.
No one's posing it. Follow the rule book first, and we'll talk, you know?
I mean, I would say that is on your, that's up to you. If that's a legal thing to do, that should be spelled out somewhere in the rule book. So that gives me 27.3 feet. Since that's bigger than 20, what we got is a home run. It's dinger time. Dingers! Is everybody okay with that idea?
Yeah.
Okay.
So you basically just kind of plug it into the story platform.
Yeah, basically. Okay. In the same situation, assuming there was no obstructions, right? That ball just cleared the fence. How far is that going to travel before it hits the ground? Right? Cleared the fence, assuming there's not like a stadium in the way, like it's your high school baseball stadium where there's nothing in the past the fence other than grass or whatever.
Right.
How far is that ball going to go? So same idea as the first problem, but in reverse, right? We need to find out how long the ball's in the air. We'll call that T sub A. And then we're going to do X of T sub A to give us the how far away that ball's going to land. So what is the height of a ball then when it hits the ground? I mean, 0, right?
Oh,
Yeah, we'll just write it. I mean, I shouldn't be thinking that hard about it. Okay, everybody's good? How do I solve an equation like that?
oh, it's like
What kind of problem is that?
quadratic.
Quadratic. How do I solve a quadratic equation that's equal to 0?
Quadratic problem formula.
Yeah, the quadratic formula. So that's negative b plus or minus the square root of b squared.
So,
Nope.
oh,
Minus 4ac
over 2a.
over 2a.
I remember that.
Okay.
Kind of.
So let's use the calculator to do that. Again, I'm going to use that fraction command so I don't have to muck around with like 1,000 parentheses.
I love the fashion command.
It's pretty choice.
It's pretty sweet. I like
So remember, I'm going to have to do this twice, one as an addition problem and one again as a subtraction problem,
Oh, yeah.
because the plus or minus. But I'll just start with the addition one.
Well,
So I did that, I got negative 0.06. Did I do something wrong? Does that answer make sense?
that looks perfectly fine. Maybe went back. Imaginary.
Well, if you think about it, this is what our parabola is doing, right?
Yeah.
Because we're starting at 3.5 above the ground. Hydrate, come on in.
Must have fallen into some sand or something.
So there's my negative t value, right? That's not super surprising. All that tells me is that the one where I'm adding is not the answer that I needed.
Right.
So I'm going to press second and enter to recover that same thing I typed in because,
Okay.
gosh darn, I don't want to type that again. I just want to go back and edit the addition to subtraction. And I got 3.64.
That looks pretty good.
That seems reasonable, right? That's further than it, or longer than it took to get to the wall. And again, I'm going to just use the calculator to do that.
Pretty cool that you can find this stuff.
Yeah, right? This is pretty neat. Pretty neat. So I'm going to do x of t. And remember, I put my x in the second spot. So that went about 469.4 feet. That's awful cool. Pretty cool. Pretty neat, pretty cool. Is that okay with everybody there? All right, we got one more example to do.
Wait, what was the value of x?
What?
What was the value of x?
The value of x,
Yeah.
that's how far the ball would go before it hits the ground,
Okay.
right? Because we cleared the fence. We got a home run on our hands, but how far is that guy going to really go?
467.4.
Which is basically, I think, what Major League Baseball does when they give you like the approximate home run distance, is they have the stat track or whatever. They get the exit velocity of the ball and the exit angle of the ball,
Yeah.
and they just do this.
Okay.
They include air resistance and stuff and
Right.
friction, but all right. One last question. It says, assuming there are no other obstructions in the way, what is the furthest distance away from your starting point that you could place the 20-foot fence and still have the baseball clear the fence? So remember what our picture looked like here. We're saying, okay, I could move this fence back to like maybe here, where the ball can still get over the fence. How far away is that? So what are we going to be doing? I want to find the time the ball is 20 feet above the ground. We'll call that t sub 20. And then I'm going to plug that in for x. That'll tell me how far away that fence can be where the ball is still 20 feet above the ground. Does that make sense to you guys? So we have 20 equals my equation for y. How do I solve this? What's up? Yeah, I got to make sure it's equal to 0 first. So we subtract 20 from both sides. Very good. Remember to use the quadratic formula. It has to be equal to 0. And then we can just use the quadratic formula. So negative b plus or minus the square root of b squared minus 4 times a times c divided by 2 times a. The good news is here that this is almost the same thing that we had before, right? The only thing that changed was my value for c. So I'm just going to go back and steal that previous piece and plug that in. And I know that I don't need the addition one, I needed the subtraction version of it. I'll find the other one also, though. So I have 3.26, or just for completeness sake, well, that's probably 2.7. .32. Which one do I want? Definitely this one, right? Again, remember what we're doing. So like, let's say this is the 20-foot line. Here we're starting at 3.5. So there's like 2 places that we cross that 20-foot line, right? Everybody's okay with that? All right, so I just need to do x of 3.27. So y-var's function, x of, and I guess I'll just grab it this way instead of doing the ands. So 421.1 feet. Actually, I should be rounding, which way? Should I be rounding up or down? I have to round down in this case, right? If I actually round it up and put the fence 4/10 of a foot further, the ball would clip the very tippy top of it, right? Because you're actually past, you know, the height there is no longer going to be 20 feet off the ground, so it'd have to round down. So this should be 421.0 feet. So this one we need to round down no matter what if we think about it from a physics standpoint. Is that okay with you guys, since it's asking for the furthest? And that's section 10.2. So at this point, you guys could do 41 through 40 something. Let me check real quick. 48. That's not going to be due this Sunday, though. This Sunday's problem set is 1 through 40. Next problem set, this 41 through 48 will be a part of. That's already reflected on my Notre Dame. I believe I got that in there. Let me double check real quick. Nope, let's do it right now then. We have virtual days on Thursday and Friday this week. You are getting nothing from me. What you're going to be asked to do is to just work on your problem set. I don't Feels like 40 problems are probably enough for the problem set. Me doing another lesson, it just means that probably we have to go over it again. So, what does that say up there? That says 320, right? The due date on the board for that. Yeah, okay. I just want to make sure I put in the right thing into the calendar. Okay. They're in there now. And I'm good. Are you guys good? Let's all be good.